For number 16, we're going to be discussing the 4 quantum numbers and how they describe the state of an electron. So the first quantum number that we designate as n is called the principal quantum number. This number says what energy level that the electron is in. So this number ranges from 1 to any other positive integer. So it can be 1, 2, 3, 4, and so on. The second quantum number is called the azimuthal quantum number, and we give this the letter n. This number is what we often call the subshell. It defines the subshells for that particular energy level. So for example, we have n equals 1. Well, the maximum that the L can be is 0 because n minus 1. For 2, the maximum that L can be is 1. However, there's also a 0 subshell for the energy level 2. For 3, we can have 0, 1, and 2. Notice that L is always the maximum it can be as n minus 1. So for 0, we call this the S subshell. For 1, we call this P. For 2, we call this D. 3, we call it F. And there are other subshell designation that you will be learning later. However, notice that for energy level 2, for example, you can have an S subshell and a P subshell. However, for energy level 1, you will not have a P subshell or D subshell. Now for the next quantum number, this is called the magnetic quantum number, and we give it ML. This is called the magnetic quantum number. This number gives the orientation of the orbital. So for example, we have n equals 1, so L equals 0. Well, there's only one orientation for this orbital because minus 0 to 0, which is there's only 1, so which is 0. However, for 2, for example, we now have L equals 1. We can have a minus 1, 0, and 1. So for the P subshell, we can have 3 orientations. We usually call these X, Y, Z. For D, with L equals 2, we can have more orientations that are a little bit more complicated. And then for F, so on, it gets more and more complicated. For the last quantum number, we call this the magnetic spin quantum number. The spin quantum number. So this number is always plus 1/2 or minus 1/2. Don't worry about the 1/2, what that means. It's just that for each orbital, there can only be it can hold a maximum of 2 electrons. One that has to be positive and the one that has to be negative. Therefore, for example, with n equals 2, we can have L equals 0 and 1. Now for the P subshell, we could have a magnetic quantum number of -1, 0, and 1. And then for each of these orbitals, we can have a positive and a negative. Therefore, for the P subshell, it can hold a maximum of 6 electrons. So there's 3 different orientations of orbitals, and then in each orbital, it can hold 2. So 3 times 2 is 6. For D, for example, if L equals 2, we would have -2, -1, 0, 1, 2 as the magnetic quantum numbers. And then for each one, we can hold 2 electrons. So this has 5 times 2. So for the D subshell, we can hold a maximum of 10 electrons. So you'll often see something maybe like this. This is a useful chart or table to have to memorize. It will help you. So the numbers in front, these are n. So for 1s, that means that this is at an energy level of the first energy level. So remember that L, the maximum it can be is 0. So that we said was S. There's only one magnetic quantum number, which is 0. And so then in this one, or it can only be in one orientation, there are 2 electrons, a positive and a minus. So for this orbital subshell, we can hold a maximum of 2 electrons. For the second energy level, you'll see now a 2p, because now with n equals 2, L can equal 1. This is what we called p, right? And so this one can have the magnetic number of -1, 0, and 1. Now this one, remember, it can hold 6 maximum electrons because each one can hold 2 electrons plus and minus. Now we'll never see something like 2D because the maximum L number is 1. It's always n minus 1, right? We wouldn't see a 2D because L can not be 2. You won't see a 3F, going by the same idea.